Our next chapter is on sequences, series, and probability. So, what we're going to be talking about in this chapter is sequences of numbers, taking those sequences and summing them, all the terms of them, that's a series, and then talking about different types of probability. Oh, looks like my hand was wanting to write more than I wanted to. All right, so first off, 8.1 talks about the basics of a sequence in a series. So we talk about what a sequence is. The word sequence is basically used much the same way as in regular English as it is in mathematics. So when you say you have a collection of listed numbers in sequence, that means the numbers are ordered so that it has a first member and then a second member and then a third member and so on. So mathematically, you can think of a sequence as a function, and that function has a domain of all positive integers. Or I guess I could write it like you would if you were to go to a college course, where you'd have the z plus in the corner. So, instead of using function notation, where I do f of x, sequences are usually used or written using subscript notation. So, an infinite sequence is where the domain is the set of all the positive integers, just like we said before, but the function values go from a sub 1, a sub 2, a sub 3, and so on until I get to a sub n, and then it keeps going on forever. A sub n is whatever the term you want to go to. It doesn't really matter. So all of these are our terms of the sequence. If the domain has of the function has the first n positive integers only, then it's a finite sequence. So infinite is going to go on forever, but if I stop at a sub n, then it's called a finite sequence, because it has a finite amount of numbers. So let's take a look at a few examples on how we work with these sequences. So let's say I have a sub n equal to 3n minus 2. This is very similar to the visual pattern problems we do in class at the beginning of class, where we take a pattern that we see visually and turn it into the equation. Well, this time I've given you the equation, you got to tell me the pattern. So what I want to find out is, what are the first four terms? So when I say first four terms, I'm not just saying number 1, 2, 3, 4. I want to say, what is a sub 1, what is a sub 2, what is a sub 3, and a sub 4. So since our function, or our sequence, is a sub n equal to 3n minus 2, all I have to do is substitute the number for the term into my sequence equation. So this would be 3 times whatever my term is. Since our term is 1, I'm going to put a 1 here. So that would then be equal to 1. Now I do the same process with all the other terms. Wherever I have an n, I'm going to put my term number in there, my step number. So here I have a 2, so I'm going to substitute 2. Here I have a 3, so I substitute 3. Here I have 4, so I substitute 4. 3 times 2 is 6, minus 2 is 4. 3 times 3 is 9, minus 2 is 7. 3 times 4 is 12, minus 2 is 10. Another type of sequence you will see is a sub n equal to 3 plus some number raised, or negative 1 raised to some number, n. That n, again, is our step number. You'd solve this the same way. Basically, this one, because all I'm doing is adding or subtracting 1, is just going to take 3 and either add 1 or subtract 1 every term. So we're going to alternate between 2 and 4. And you'll see that when I solve this, a sub 1 would be 3 plus negative 1 to the first. Well, that's the same as 3 minus 1, which is 2. A sub 2 is 3 plus negative 1 squared, which is 3 plus 1, which is 4. A sub 3 is 3 plus negative 1 to the third, which is 3 minus 1, which is 2. And you'll see this pattern will continue to oscillate back and forth between 2 and 4. Oops, that should be a plus 1. So we get 4. Alright? So anytime you get a sequence equation, all they're asking you to do usually is to write the first few terms that they want you to find. Now, if we just list the first few terms, that is often quite often not sufficient enough to tell us a unique sequence. We have to know the nth term. So if I just tell you I have a sequence that's 1/2, 1/4, 1/8, 1/16, and so on, that's not enough to tell us the sequence. We have to know what the equation is to find any term in the sequence. So that's where we bring in the nth term. And this is where we have an n in my sequence term. So anytime you see one, or anytime you see a term that has n in it, that's called the nth term. So what's tricky is taking what we've done, which is like the visual patterns that we do, and writing the equation for it. I won't go into that since we've done a lot of that in class, but just know that this is the nth term. For this equation, actually, or this pattern, I've already shown you what it is. It's 1 over 2 to the n. Basically, you're going to relate the term number to the actual term. Okay? So in this situation, our first term is 1/2. So for term 1, we have our n is 1, and our term is 1/2. So how do I turn 1 into 1/2? Well, that's the same as multiplying by 1/2. For our second term, we have 2, right, in our second term. So that's 1/4 is what we have for our second term. And so 1/4, how do I turn that 2 into 1/4? Well, I multiply by 1 over 4 this time. So I can basically rewrite this sequence as 1 over 2 to the first, 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the fourth, and so on. And that's where we get that from. We notice that pattern. And so that's where we get the equation for it, the nth term. Some sequences we have are what we call recursive. And they're defined recursively. To define a recursive sequence, you have to have one or more of the first few terms. You have to know what they are. All of the other terms in the sequence are then defined using the first few terms. For example, the Fibonacci sequence is a prime example of a recursive sequence. If you don't know, the Fibonacci sequence starts out, our first term is a sub 0 equal to 1, then a sub 1 equal to 1, then a sub 2 equal to 2, or actually every term after that, I should say, a sub k is going to be equal to a sub k minus 2 plus a sub k minus 1. Basically what we're doing here is we're starting off with the first two terms as 1, and then every other term after that I add the term 2 before it and the term 1 before it. So for example, we start off with 1 for a sub 1 and a sub 0. A sub 2 is going to be a sub 2 minus 2 plus a sub 2 minus 1. Well, a sub 2 minus 2 is the same as a sub 0, and a sub 2 minus 1 is a sub 1. Well, a sub 0 was 1, and so is a sub 1. So this is the same as 1 plus 1, which is 2. And so I would continue to use the recursion formula to find the next term in the sequence. And you'll notice it's basically adding the two previous terms to get my next term. So 1 plus 2 would be a sub 3, which would be 3. Just a coincidence that 3 is the same as the third term, or the fourth term. A sub 4 would be 2 plus 3, which is 5, and so on. You just add the two previous terms to get my next term. Next, what we need to talk about is factorials. Factorials have a lot of applications in probability, which we will get to later this chapter. But it's also a type of sequence. This types of sequences have to do with what this notation is dealing with. So if I have an n positive integer and we have this exclamation point, that means factorial. We read it as n factorial. This n factorial is basically saying whatever my integer is, I'm going to multiply all the numbers up to that number together. So n minus 1 is the number just in front of the number n, and n is my final number. Basically, you're going to take all the numbers from the number you have all the way down to 1 and multiply them. Now there is a special case. You're thinking, well, what about 0? Because n is a positive integer. 0 is a positive integer. So 0 factorial is equal to 1. That's a special case. Obviously 0 times nothing is still 0. But because we don't really have anything, I mean, we can define it as 1. It's just defined that way. So for example, 0 factorial is equal to 1. 1 factorial is also equal to 1. 2 factorial is the same as 1 times 2, which is 2. 3 factorial is equal to 1 times 2 times 3, which is 6. 4 factorial is equal to 1 times 2 times 3 times 4, which is 24. So you get the idea. Let's see. That's factorials. Basically, the way that factorials work is anything you multiply or add, you can do that outside of the factorial. So for example, if I have 2n factorial, I can rewrite this as 2 times n factorial, then find the factorial, which would be 2 times 1 times 2 times 3 times 4 all the way up to n. And then once I'm done with that, I just multiply it by 2, and that's my answer. So basically what I'm saying here is you have to follow the order of operations. So this is different than this. If the 2 is outside the parentheses, you multiply it afterward. If the 2 is inside the parentheses, this is the same as saying 1 times 2 times 3 times 4 all the way up to 2n instead of n. So I can also use factorials as writing my terms of a sequence as well. There are some special things with factorials. Let's say I have 8 factorial over 2 factorial times 6 factorial. This wouldn't be able to just reduce perfectly because I'll show you why exactly. So 8 factorial is the same as 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. And 2 factorial is the same as 1 times 2. And 6 factorial is the same as 1 times 2 times 3 times 4 times 5 times 6. So because the way the rules of division, I can reduce 1 through 6 on the top and bottom, and I'm left with 7 times 8 over 1 times 2, which 1 times 2 is just 2. Now 2 goes into 8 4 times, so we get 4 times 7, which is 28. Another way to think about this is I can rewrite 8 factorial as 6 factorial times 7 times 8, and then leave the 2 factorial and the 6 factorial out like that, or expand out the 2 factorial and leave the 6 factorial. And then I can just reduce the 6 factorials, and then I don't have to write as much. I have that 7 times 8 on top and the 2 on bottom, which obviously is the same as 28. So it's just a quicker way of reducing. Another thing you can do is also do this without numbers, just dealing with with letters instead of having values for n. So let's say I have n factorial over n minus 1. This one might be a little bit tricky to do without, but you notice n minus 1 is just 1 less than n. So if I expand out n factorial, this would be the same as n minus 1 factorial times n divided by n minus 1 factorial. Those n minus 1 factorials reduce, and I'm left with just n. Now I could expand out the n minus 1 factorial as well, so 1 times 2 times 3 all the way to n minus 1, but that's writing I don't really want to have to deal with. 2 more things for this section. Summation notation. I like saying that, it's fun to say. Summation notation. Oops, spelled it wrong. Summation notation. Okay, summation notation, or sigma notation. Sigma. Sound like a movie you heard of? I don't know. Anyway, I digress. Sigma is from the Greek letter sigma. It's like a funky E looking thing. I'm sure you might have seen it before. But basically, we write sigma notation or summation notation using the uppercase Greek letter sigma. And basically what this is taking the terms of a sequence and adding them together. So let's say I have the sum of a sub I from the letter I equal to 1 all the way up to n. What this would tell me to do is take a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 all the way until I get to a sub n. I'm going to add all of these terms together. Just a little clarification, I is the index, so that basically tells me where I start. N is the upper limit, that tells me where I end. And 1 is usually the lower limit. We usually start at 1. You can start anywhere, but we usually just like to know, starting out at 1, what our answer is. Okay, so sigma notation, this is basically what we're doing. Whatever the term is, a sub I, it could be anything. We can put anything in there for a. It doesn't matter. What matters is whatever I do, I'm going to substitute my letter I or K or N or H or whatever it is, whatever that value is equal to, I'm going to do it all the way up until I get to the nth term, and I'm going to find that many terms and add them together. So let's look at a value real quick, or an example. So let's say I have the sum of 3i from I equal to 1 up to 5. Basically what this is telling me to do is I'm going to do 3 times 1, because that's what 3i is, 3 times I, plus 3 times 2, plus 3 times 3, and plus 3 times 4, and plus 3 times 5. So I do all 5 of these together. Now since they all have 3's, I can factor out that 3, and then just do 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. And then 3 times 15 is 45. That's one way to do it. Another example would be if I want to find the sum from k equals 3 to 6 of 1 plus k squared. What I would do is where I have a k, I would start off with 3. Here's a prime example of us not starting at 1. But I would then do 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1 plus 6 squared. And then I'd just solve that problem. So then I'd have 1 plus 9, which is 10. 4 is 16, so it'd be 1 plus 16, which is 17. 5 is 25, so I have 26. 6 is 36, so plus 1 is 37. And all these add up to 90. So that's kind of how you do it. Okay? Next, what I'd like to talk to you about is what a series is. But before that, we need to know a few properties of sums. The first property of sum is basically what you would think it is. If I have a sum from 1 to n of a number c, where c is a constant, it's just a number, only a number, nothing else. No I. You'll notice there is no I next to the sigma notation. Basically what this is saying is, however many n's I have, I'm just going to multiply it by c, because that's what I have to add up. So this would be the same as c times n. The second property is if I have I equal to 1 all the way to n, or the sum of numbers from 1 to n of c times a sub I. In this situation, c doesn't change the value. I could multiply c by a every time, or I can factor out that c and then multiply by the sum of all the a sub i's. So this is the same as saying c times the sum of a sub I from I equal to 1 all the way up to n. Again, in this situation, c is a constant. The third property of sums is if I have a sum from 1 to n of two values, two different types of terms added together, this is the same as the sum of each one from I equal to 1 to n added separately from each other. So I find the sum of the i's, or the a sub i's, and then find the sum of the b sub i's and add those together, and that should be the same as if I were to add a sub I, all the a sub i's and all the b sub i's together, and then add those together at the end. So a sub 1 plus b sub 1 would be the same as all the way to a sub n plus b sub n would be the same as a sub 1 added to a sub all the way through a sub n, and the same for b, I would then add those two together. Sorry, that might be a little confusing, my language I'm using here. But basically, it should be the same value. And then the same thing works if I am subtracting. Again, same thing works if I'm subtracting. So if I have two terms inside the parentheses, that would be the same as if I were to, then subtract them on the outside. Alright, so those are the properties of sums. Our last topic for this video is series. A series is essentially when I sum the terms of a finite or an infinite sequence. So it's a sum of the terms of a finite or infinite sequence. So a sequence is a list of numbers. A series is a sum of those lists of numbers. Alright? If I am finding the sum of a finite series, or a finite sequence, so I'm only finding the first n terms, that's called a finite series. So the finite series is if I go from a sub 1 all the way to a sub n, and I stop. I don't keep going. So my n value stops at a sub n. This is a finite series. So I'm going from I equal to 1 to n for a sub I. So my terms for a go from a sub 1 to a sub n. I add those all up. That's a finite series. Another name for this is a partial sum. The reason it's a partial sum is because I'm stopping. Technically, all sequences are infinite. So I could continue with the same sequence or the same series, but I'm choosing to stop at a certain number n. And then if we have an infinite or a finite series, I also have an infinite series. So the infinite series is like saying I'm going to add up every term forever. What should that equal to? I'm going to add up all the terms of the infinite sequence and don't stop. So this would be a sub 1 plus a sub 2 plus a sub 3 all the way until I get to a sub I, which is whatever my term my index is, and then I keep going. So here I go from 1 to infinity instead of n. Infinity, as you know, is not a number, it's a concept. So there's really no stopping here. So on the next slide I will show you a couple applications for this. I will do a partial sum and an infinite series. So let's say I have the infinite series from I equal to 1 to infinity of 3 over 10 to the I power. We have to find the third partial sum and the sum. Sorry, my stylus isn't working. Alright, so when it says the sum, I just have to find the infinite sum. I find all the numbers from I equal to 1 to infinity and I add them all up. For the third partial sum, however, all I'm doing is 3 from I equal to 1 to 3. Instead of writing infinity, I would have the same sum. Instead of writing infinity, I would have the exact same sum, but I would have, 1 to 3 on top. So my first term would be 3 over 10 to the first. Second would be 3 over 10 to the second. 3 over 10 to the third. And I would stop because it's a partial sum. It goes from 1 to 3 and that's it. 3 over 10 to the first is the same as 0.3. 3 over 10 squared is the same as 0.03. And 10 cubed is 1,000. So 3,000ths would be 0.003. And these all sum to equal 0.333. And that's it. Your term is done. You're done finding the sum. So part B is find the actual sum. So I'm actually going to find the sum from 1 to infinity of 3 over 10 to the I power. Man, my stylus really doesn't like me right now. That looks better. Okay, so again, the first 3 terms that we had before are going to stay the same. But I'm not going to stop with the first 3 terms. I'm going to keep going until I want to kind of figure out what the pattern is going to be like, or what it's going to get closer and closer to. Well, if I kept doing this forever, 3 over 10 to the first, again, is 0.3, then 0.03, then 0.003, then 0.00003, 0.00003, and I would keep going for infinity. Well, if I add them all up, you'll notice they all just occupy one spot. What fraction do we know is a repeating series of 3's? A repeating decimal of 3's? Well, the only thing is 1/3. So if I were to take the fractions from 3 over 10 to the first all the way out to infinity and add them all together, this would be the same as if I were to have the fraction of 1/3. So that's series. There's lots of other applications for this. For example, in population is another example, but I think that's all for this video. Very long video. Hope you enjoyed. Bye.